Alrighty, welcome back everybody. It's your man, Math Man Mr. coming to you live from Summit Academy. In this video, we are working still on our polynomial functions. And the last couple videos I made here, we've been talking about, where those x-intercepts on our curve. And so we really focused on, where it is on the graph. And last time we talked about, where is it in the equation and how do we get it in the equation. And now let's kind of talk about what kind of descriptors and information we can get from a polynomial function. And so we'll talk about what the degree looks like, what the exponents look like, what the function looks like, but we'll see how it works. But it looks like this. So let's try to come up with an equation that has roots at 1, 0, -3, 0, 4, 0, and -2, 0. But it also passes through the point 5, 0. And so this is what we can do. We can kind of draw out our general equation. So our general equation is f of x equals, and we have a, which is our leading coefficient. We have x minus b times x minus c times x minus d. And let's say, since we have 4, let's go the whole way out to g, just for, you can use whatever letters you want, but for the most part, we're just saying, hey, I have 4 x-intercepts because I have 4 different points where it has the y value is 0. I need to figure out what those pieces are for our equation. We don't know our leading coefficient, so we're just going to be able to solve for it. So now I substitute in my x-intercepts for my letters here. So for example, excuse me, so this was my general equation. Now I'm going to sub in, so I'm going to say I have f of x equals, I don't know what a is, but I have x minus 1, parentheses times x plus 3, parentheses times x minus 4, and we have our last point is x plus 2. So again, notice how they're not in a particular order. Again, I can change the order of these groups, these little packages, these sets of parentheses. I can change the order of them because we're multiplying them together. And so, like in the last video, I talked about the commutative property of multiplication. We're saying, I can change the order of these sets of parentheses. So now, excuse me, fighting off a cough here. We can say this. We can say, all right, well, if we have these are, most of our equation. We have everything in the equation we need except for that leading coefficient. So we have 95% of our equation just by plugging in, those x-intercepts. So now what we're going to do is I'm going to say this. I'm going to say this. Let's say substitute. Let me try to write that again. There we go. Substitute let's say that this extra point, which actually is already x-intercept. Sorry, I messed up. So let me actually go back. I kind of forgot that I wasn't paying attention here. I have actually 5 x-intercepts because I need to go through that point of 5, 0. So I'm going to say I have, this is x plus 2, and then I also have x minus 5. So for the most part, you should be able to plug in that extra point, kind of like how we did in the semester 1 class of Math 3. But for right now, all we have to have is just this. We're going to say, we can let a equal 1. And we're going to say, okay, this is going to be our function. So I'm going to type it out here. I'm going to say f of x. Almost typed in another point, but luckily we caught it because I said, hey, that's equal, y value 0. So that's actually another, we're going to say 1. I'm going to let a equal 1 just for this one, just because it doesn't have, an extra point for us to check. we're going to say a equals 1. I'm going to say our sets of parentheses, we have x minus 1 times x plus 3 times x minus 4 times x plus 2 and x minus 5. Okay, so I have 5 points that it goes through on that x-axis. And I know these are x-intercepts because they are where the y value equals 0. All right, moving on. So what we're talking about, we'll be able to identify the degree of a polynomial in both the graph or the equation form, and we're going to be using that language of describing. So when you're looking, again, you can also use our wonderful vocab sheet that I gave you, but it looks like this. We can just talk about what the degree is of a polynomial. And remember these definitions. We're saying a polynomial is a multi-term. This is what poly means. Poly means multiple, and then nomial means term. So multiple term equation. So if I'm looking at this first equation, or this first expression, I should say, I'm talking about I have negative 2x plus 7. I'm looking at the highest exponent in this equation, which means I have to have an exponent of x, and even though I don't see a number here, that's okay because it's implied that it is a 1. Because if it was a 0, it would be like this. It would just be blank. So if I have x to the power 0, that's just 1, which we wouldn't have to write. So if I have x to the first power, though, I do have to write an x. And then we can have our quadratic function here. We have 4x squared minus x plus 6. I know this is a second degree polynomial because I have an exponent 2. The highest exponent in this equation is 2. Again, I'm not looking for the highest number. I'm looking for the largest exponent. Specific word here is at that exponent. So a lot of people would say, hey, well, why isn't it 7 or 6 in those equations? I'm not looking for the largest number. I'm looking for whatever the highest degree is, meaning the highest exponent. So if I'm looking at this last one, I'd say, well, it's in order. It's in standard form, meaning it is in decreasing order. So notice how it goes. Exponent 3, exponent 2, exponent 1, exponent 0. And we can have more examples past that, because we can have higher degree polynomials, but we're just looking for, if it's in standard form, I'm looking at the highest exponent. So on that last one, it would just be 3. That'd be a third degree polynomial. However, when it's in factored form, which another example of a factored form equation is this general equation, or sorry, not this general equation, this equation right here. Notice how it's factored out because I don't have any exponents anywhere. I just have multiple sets of parentheses, but for this example that we did in the warm-up, I would also want to label, hey, this is degree 5 because there is 5 sets of parentheses. I'll try to write that again, parentheses. So I'm just saying, I have 5 sets of parentheses, on this right side of this equation, because I'm saying, hey, if my function f of x is on the left, but I'm saying, well, in terms of x on that right side is my equation. So I can have 5 sets of parentheses. I don't have any exponents, and so I just say the degree is 5. All right. So let's look at that factored form definition. So the degree of a polynomial in that factored form. Again, notice how it's sets of parentheses. So I would say this is a first degree polynomial just because it has one set of parentheses. I would say this is another example of a quadratic because it's a second degree polynomial. Notice that it has 2 sets of parentheses. Or you can also have a exponent 2 in it. So notice how on this example right here, I'm saying I have f of x equals, in parentheses, x minus 2 squared. So since I have my exponent 2 in this one, that still counts as a second degree polynomial. So it's either form. It can be, in sets of parentheses with an exponent, but we're just looking at that total degree. Another example it has at the bottom here, this is a third degree polynomial because I have 1, 2, 3 sets of parentheses. Or another example is this. Even though I don't have, multiple things here, I can say, well, I have x to the first power and I have x to the second power, which is a total of 3. So I will have to add some of these together. So if we have multiple sets of parentheses, maybe some double roots in there because of the exponent, you can see that we have, a degree 3 polynomial just by adding those together. All right. So let's try these out. So it says, what's the degree of the following polynomial? So I have it in standard form because I don't see any sets of parentheses. So I'm looking at the highest exponent. Well, that's usually in the front. So I'm going to say, please click away. Okay. Okay. So when I'm looking at this exponent, I'm saying, hey, the highest exponent that I have in this equation is going to be 4. So my degree is just going to be 4. It's getting real simple. Again, when you're trying to identify the degree of an equation like this, again, it's really simple to be able to look at that, either the sets of parentheses or the highest exponent. So similar idea with this, a little bit different looking of an equation. We have a factored form equation because I have multiple sets of parentheses, but I'm saying this, okay, I have x to the first power, I have x to the second power, and I have x to the first power again. So since it's in factored form, I have to add them together. So I'm going to say, keeps highlighting. There we go. I'm going to say this. I'm going to say I have x to the first plus x to the second is 3 plus another x to the first power is going to be 4. So I have to add that total number of exponents together. So if it's in factor form like that, just be very careful. Take your time. Again, I'm saying I have 1 plus 2 plus another 1 is going to be 4. All right. Similar idea. Be able to add all these up together. So I have how many sets of parentheses? I got 1, 2, 3, 4, 5 sets of parentheses, with that last one being a double root. So I counted twice. So let's count again. I'm going to say 1, 2, 3, 4, and then I say 5, 6, because my total degree, my total number of exponents is going to be 6. For this one's a little weird. This one's just, I don't have any x's here, so I'm going to say that's going to be 0. So I can also say how many times do you see that change? Well, if I was to graph it out, I'd say it changes 0 times. Similar idea, this is just a first power polynomial just because I have 1x to the first power, so it's just going to be a linear equation. All right, so now if it's on the graph, so let's do a little bit different here. So when we're talking about equations or our polynomials on the graph, we have to first find the degree from a graph. Or excuse me, we're finding the degree from a graph. First, we're going to say we need to find or identify the number of changing points. So that's kind of what I was talking about before. We're trying to say, okay, how many times does it have a change, whether it's going from increasing to decreasing or from decreasing to increasing? We can say to highlight the areas on the graph which it appears to switch directions, like a mini hill or valley. So if you're thinking like a map or something like that, we can say, hey, I need to identify where those hills and valleys are, or the turns in the road. So I'd say I have 1 changing point, 2 changing points, 3 changing points, 4 changing points. So I can identify really simply. Again, you'll get multiple practices with this, but I want to be able to identify where my function or my polynomial graph is changing. So I'd say, at these points is where we have changing points. So I'd say changing points, I'm going to call it CP here in a second, but we're going to say changing points is going to be equal to 4 because it changes 4 times. Let's see if we're right, and we're good. Okay, same picture now. Same picture. It says the degree will be the number of changing points plus 1. Again, this kind of works in towards, derivatives and some pre-calculus stuff that you don't have to worry about. But again, if you want to research that on your own, you certainly can. But we're saying, what is the degree? Well, we're going to say, let's write this down. We're going to say, let me do a different color here. Let's say degree. We're going to say degree is equal to, make sure it's G, degree is equal to changing points plus 1. So CP plus 1. So we're going to say our degree for this one, we said we had 4 changing points and we add 1 to it, so our degree is going to be, our degree is equal to 5. So I'd say my degree is equal to 5. And we're good. So all I'm really asking you to do in this unit is be able to count and add. So it's really simple to be able to, know a lot of these things and be able to perform a lot of these things just by getting, some simple points here. All right, moving on. So now it says the degree will be the number of changing points plus 1. We said the degree is 5, which means the equation has 5 roots. However, when I look at the graph only shows the equation with 3 x-intercepts. If I look at those 3 x-intercepts, let's say, I got 1, 2, 3 here. Those are really easy to identify. It says the remaining 2 roots are called complex or imaginary roots. What that means is, so if I look like this, I can say, okay, I can say count, let's say total degree. Say count total degree. We're going to say count, change colors here. Let's do green again. I say count x-intercepts, which we said our total degree was 5. We said our total number of roots is 5. And so we say our x-intercepts, we count our x-intercepts. I say we have 1, 2, 3. And so I have to subtract that to get our remaining roots. So we said, hold on, we say our x-intercepts was 3. So our remaining roots, we do, let's do red. Lets me. Yeah, okay. Let's say remaining roots is just going to be simply, we just calculate, we just do 5 minus 3. We're going to say that equals 2. So that means we have 2 complex roots. 2 complex roots, meaning we can't really see them on the graph as easily as it is, but we can be able to find, and identify how many there are. So that's going to be the max question I ask is find the total degree and find the types of roots that are in that picture. So let's try a different one. All right, so it says, what is the degree of this polynomial? So I'm going to have this question a bunch of times. All right, so find the total degree. I need to find the total number of roots, which I need to find the changing points. So I'm going to say I have 1, 2, 3 changing points, which means my degree, I add 1 to it to get 4. So my total degree for this polynomial is 4. Then we're going to say, okay, well, if we're looking at that, how many real roots does this polynomial have? And how do we know that? So I say, how many real roots? Let's say this polynomial has 2 real roots because it has, or let's say it hits the x-axis in 2 different places. So I should be able to, just find out what it is just by looking at the graph. Again, it's really simple to be able to find and identify what they are. Let's say how many imaginary roots is it? Well, let's think. We said we had 4 total as our degree, or our number of roots, but we only had 2 x-intercepts. So I can say, all right, since we have 4 let's say 4 have a degree 4 polynomial and 2 real roots. This means that we have 2 remaining roots, which we can say are complex roots. So we should be able to, find out, count the number of chaining points, add 1 to it to get our degree. Once we have our degree, our total degree, we can find, okay, I can easily count and identify where our x-intercepts are. We subtract the 2, and we get 2 remaining roots. So I say 4 minus 2 is equal to 2, which tells me I have 2 complex roots. All right, last couple here, just a reminder, kind of driving home the idea, if my degree is 1, that means I have 1 total number of roots. If my degree is 2, I have 2 total roots, 3, 4, 5, 6, 7, so on and so forth. So I can keep going with this, but we're saying, whatever the degree is, that's going to be your total number of roots. So just make sure you're remembering whatever our degree is equal to the total number of real roots. Okay, last part here. It says, here's next ticket. It says identify the degree, the real roots, and the imaginary roots. So try this one out. Again, be sure to check with me. And as always, super slam that subscribe button.